Here we have a 5-meter long beam. That's this rectangle here that I've labeled beam. It's just one beam. And it has a distributed load given by W of x equals 100 minus x squared newtons per meter. And this red line, or this red curve with the arrows, the red arrows pointing down, that indicates the distributed load. So what that means is that as x moves from 0, which is the left end of the beam, to the right end of the beam, as x moves along, the weight or distributed load changes. Right? It changes with respect to this function W of x. And our goal is to find the total force on the beam. So in general, dF, d force, is equal to force times dA. Now in our special case here, dF is equal to W of x times dA. Now remember, this is we're thinking of this as a one-dimensional object. Even though the beam does have some y dimension, we'll think of that y dimension as 1. So this will be 1 times dx. You can think of the width of this arbitrary rectangle that I have here in black. The width here is dx. So with that in mind, we see that dF is equal to our distributed load, 100 minus x squared, times dA, in this case dx. And so to compute our total force, we'll use an integral to add up all of the arbitrarily small rectangles over the course of the entire beam. This will be from 0 to 5 dF dF, as we know, is 100 minus x squared dx. Doing the math here, let's see, we've got 100x minus, x cubed, right? X cubed over 3, evaluated from 0 to 5. This comes out to 458.3 newtons. Now remember, let me just show you something with the units real fast. The units for W of x are newtons per meter. So we have newtons over meters here. dx, remember, dx is in meters. Right, 'cause remember this was a 5-meter long beam. So you can see that these will cancel, and that's how we get this newtons here.